Welcome back, everybody. We're going to move right into the material panel, Going Small to Think Big. It will be moderated by Yuneng, who we met last time, and there will be 3 other people on the panel along with her to talk about the future of materials by taking inspiration from living systems.
So hi, everyone. We're back with a group of experts from both academia and the industry, and then they will tell us more about all the buzzwords that I just mentioned, like circular economy, decarbonization, smart materials, or self-healing in terms of nature-inspired material. So how about we start with having a brief introduction of each of you guys. Maybe we start with Doug.
Sure. Glad to. So my name is Douglas Ramsey. I'm a managing partner with Axial Global Advisors. I'm going to be the most difficult member of the panel. My day job is working with governments around the world. I'm currently in Germany working with the Fraunhofer Institute, helping find innovations, whether they're material innovations, digital innovations, and bringing them to scale, which of course is no small feat. And when we're talking about biomimic innovations, we tend to double the challenge. So with that, I'll go around the horn. Why don't send over to Julian?
Okay, my name is Julian Vincent. I'm a retired academic. I spent about 40 years, I suppose, looking to a very large extent at the fracture mechanics of biological materials. And that's all biological materials, plants and animals, and also sundry aspects of the way they live. And I suppose for about the last 20 years, so the last half of that period, I was very interested in how one can move ideas across or concepts across from nature into some sort of technology. Unfortunately, being an academic, I didn't have enough time to do that properly. So in the last 12 or 13 years that I've been retired, I've been sorting out a way which seems to be becoming quite reliable. The nice thing about it is that it's quite closely related to Darwinian ideas of evolution. And also the system comes from an engineering context. So it's a pretty unified bridge, I think.
All right, then.
Lorenzo, yeah.
Yeah, I'll go next. So my name is Lorenzo Mencatelli. I'm R&D director for Helicoid Industries. We are a young startup based in California, developing biomimetic technology for advanced composite materials. My background in it is aerospace engineering, and I started my academic career in developing bio-inspired advanced composite materials, looking at ways of leveraging on failure mechanisms and microstructural features that can be found in several natural microstructure to develop more damage tolerant and especially impact resistance composite materials. And now with Helicoid Industries, we have developed a technology platform to try and apply this concept to a wide range of industries, from automotive, aerospace, down to sporting goods applications.
Nice. Can I start by a very simple question? So in automotive industry, what is a good material innovation?
Trams.
I'm sorry, say again, Julian?
Trams. Not cars, trams. The electric car won't last. And trams are far more controllable. There's much less pollution. They actually run on time. And they can be made, as you'll find in Germany, to tie up with the rail system as well, very, very effectively. And you find that also in most European capital cities. Vienna, for instance,
as provided that right trend. But now we have another problem that we need to bring in, which is sustainability of these structures. And while it's fairly easy to recycle aluminum, for instance, and this is what most of our cars are made of when we're talking about aluminum, is recycled aluminum, then it's a bit more difficult to talk about recyclability of fiber-reinforced composite materials. And this has been a problem that now has found quite a good solution. And the first one that comes to my mind is a higher extent of natural fibers material and bio-based materials in this automotive component, not just as an interior design of the car, but also in structural component. And there is a lot of attention in this direction. And where biomimicry could actually help us in this is trying to improve the performance of these natural fiber components, because it's starting from a low performance constituents such as a natural fiber compared to a carbon fiber, and trying to find the right fiber architecture or design of the material to actually improve the performance of that material and lead to equivalent performance to carbon or glass fiber composite solution. And there is a lot of work in that. In the US, the DOE is putting a lot of focus on that. I think we can already tell that Helicoid has just got a phase 1 SBIR grant in trying to improve indeed natural fibers reinforced composite performance through biomimicry knowledge and features. So it's a real trend. It's out there, and we're very happy to be part of it.
Hey panel, this is Trisha from Great Lakes Biomimicry. I just wanted to let you know we lost our feed for about 5 minutes. So we heard the first question and then it blanked out until Lorenzo was answering. So just wanted you to know that we missed out on that.
Oh,
We're good now.
Can I suggest a problem, though, which occurs with auto transport on the road? And that is that there's something like, latest I saw, 3,600 times more particles produced, rubber particles from tyres, than from the exhaust per unit distance travelled. And those particles are going to be fairly small, about 2.5 microns in size. And remember that you're not allowed to use carbon fiber, for instance, if the diameter of the fiber is less than 5 microns, simply because of medical problems with causing cancer. So we do have a problem there. I think there's a chance of using some of the ideas from the way the nasal systems work in desert living animals, for instance, where the tubes that the animals breathe through are fairly large and don't really disturb the speed at which the air goes through them, but there is quite a lot of deposition of the particles. I'm not sure how that works. I've seen one paper about it, and they've built models with 3D printing, but I don't think they've analysed it well enough to be able to scale it up or anything. And the other problem, of course, is where do you place something to be able to capture particles like that underneath or behind the chassis of the car? So you'll need to have a pretty good idea of what the airflow is like under the car. Now, when you consider the amount of pollution which comes out of road vehicles, certainly in Britain, nobody seems to bother about that, or not least in government, but then they're all charlatans. So it is something which needs to be taken fairly seriously, I think. There was a case about 3 years ago of a woman whose child died through pollution, and she managed to bring the case to court and got substantial damages.
Okay.
Yeah, car dust pollution has been really heated these days and discussed. I'm wondering, would there be a material solution that does not shed particles at the first place?
No. In order to gain traction, you have to generate friction. In order to get friction, you have to break bits off the material, because that's where the energy goes, into fracture surface. So there's no way of doing it. You can cover the road in ice, in which case you won't get anything off the tyre, but you won't get anything out of the car either.
Let's see. Well, next question, it'll be more broad scale as well. I'm wondering, from all of your perspectives, what is the roadmap of nature-inspired material development in the automotive industry, or timeline per se?
I can take very briefly on that. I think that one big aspect, as Doug mentioned also during his introduction, is scalability of these solutions and cost. Because in automotive, it's really the priority is cost, then cost, and cost. And if you are not able to provide a solution that is cost competitive over high volumes, then it becomes really a challenge to make a case for why this solution should go into a car.
Yep. So yeah, of course, I'm going to echo that observation. But what does get interesting is we're getting into a new transportation era where we do have self-driving cars. We're going to have autonomous zones within cities. We're already seeing it here in Europe with small buses in Switzerland, Germany, and Spain. But it changes what's allowable, and it just starts to change the design parameters. So if you're not making a car to last 10 years and you're in a different crash and safety environment, you start to get to play with different technologies, and also the volumes are going to reduce significantly. And this is where I'll go back to Julian's comments. Trams, okay, other ways to think about urban mobility. So the automotive industries are making a significant shift. Looking at what does a future look like in 10 or 15 years, where production's in half, and the use profile becomes different. It's not years owned; it's miles driven. And the safety parameters become different because now we have auto braking. It opens up new material innovations. You start to think about, can you make smaller lots of more artisanal vehicles? Now nature design is right back in. Because now you can do really interesting things with generative design with very conventional materials. As long as you've got the appropriate AI engine that's trained to be able to capture all of the dynamics and forces. And I already see this happening. It's happening at GE. I worked with Toyota Motor Group a couple years ago back in Nagoya. They were exploring all of these applications, and they started in their racing division, saying, how do we push this to the edge so we can bring it back home and we can get a smaller, more compact, more eco-friendly car on the road? And generative design, nature-inspired design, they went straight to it right from the beginning.
There's another aspect I think we should think about if we're looking into the future, and that is that there's going to be a lot more working from home. Instead of, which again is a negative effect. I think it's important to think of negative as well as positive effects because, after all, these industries require a fair amount of investment, and people want to know what their investment is going to get for them. Working from home could be really quite produce a different scenario in terms of travel, because I was listening only yesterday to a podcast where the guy was saying, well, it's all very well people from outlying towns and villages moving into London, for instance, where the main offices are, but they'd much rather live in the villages. At the weekends, they go back to the village where life is much more peaceful. So what if they can do all their work from where they would prefer to live, and maybe go into London only once a week or once a month or something like that, just to catch up on a few essentials and to make sure that it's they who are doing the work and not somebody else. So I think you need to take that sort of thing into account as well.
So it's an interesting observation because the automotive companies were already making this shift with the anticipation that there would be less miles driven, there would be less consumption. This is a post-COVID lesson learned. We had all the technology to go remotely, and a lot of people liked it. So they're not going back to the office, and they don't have to go back to the office necessarily. And then now we're in a COP26 environment. We need to start thinking about scope 1 and scope 2 immediately. That's our carbon that we're generating, but the automotive companies have this very, very long tail into scope 3. And scope 3 gets into primary materials production. And if you want to identify where the carbon is being made in manufacturing, it's being made mining and smelting and refining, rolling, casting, I can go on. And tracing all of that data and getting it into the car manufacturers so they can just certify green cars. We got big challenges in front of us, but at least we have the wicker work of a workable framework.
Nice. Sounds like good news. I remember talking to Julian, you've been telling us about how actually biomaterial or biomimetic materials functions in a way that is really different from traditional manufactured materials. And we need to create
steel. You want a material which is stiff and also tough, you go for a bit of metal. And the specific gravity of metal is about 8. But if you look at natural materials, you can get something like mother of pearl, which is getting on for as stiff as steel, but it's made out of chalk. And it's made out of a certain amount of protein. And so the specific gravity of mother of pearl is the order of about 3, I think, 3 to 3.5, which is typical for a ceramic. But if you then look at the fracture properties of mother of pearl, you find that they're superior to steel. The same can be said of wood as well. And the reason for that is not the component materials. Well, obviously, chalk is a very weak material, but the way they're put together. And the way in which, and this is my big thing about fracture, if you understand fracture, you understand most of the things about a material. The way in which the material responds to fracture. If you work in an engineering department, which I have done, you find that everybody is talking about the crack initiation and stress concentrations at the tip of the crack and stuff like that. And you learn to do the sums, which tell you how large a crack you can get, what the diameter of the tip of the crack has got to be before you run into trouble, and all that sort of stuff. But that deals only with the initial part of the problem, because there's a second component into controlling fracture, which comes in, and that is the work which is absorbed in creating new surfaces, and in other words, extending the crack. So you can start off from the engineering point of view, but they'll never work out how it is that this crack can be stopped extending so far. Sometimes they put in little crack breakers and things like that. But with a biological material, that tends not to happen. So something like mother of pearl gets its very, very good mechanical properties from its ability to absorb energy, which is coming from whatever the threat is, which is causing it to break. And they control, therefore, the way in which that fracture propagates by controlling the structure. Now, what you've done here is to make a material which is very, very tough. It's about, well, depending on how you test it, it's something like 3,000 times tougher than any of the components which are made from it. And at the same time, you are doing this using rubbish materials, which are very, very easy to recycle, of course, but using structure. And so whereas in technical materials, you tend to mine metal, as we've just been hearing, which you can recycle, of course. In biology, you tend to spend more time looking at the structures that you're playing around with and using those structures to provide very, very high toughness materials. Now, if you're thinking about automotive and having crashes of one sort or another, then toughness is a very important characteristic, because you're trying to absorb energy into the chassis and the surrounding bodywork and places like that before it actually gets through to the passengers. And preferably, you'd like to absorb that energy fairly slowly so that you decelerate the passenger compartment rather than throw the passengers around. So I think from those 2 points of view, one, that the materials are not so important with biology, it's the structure, and the way then the structures work to absorb energy rather than simply stop a crack progressing. I think those two things are aspects which aren't really taken up by industry at the moment. Lorenzo is taking up some of that with the fibrous composites that he's using. But I'm trying to get him to work on some stuff we were doing years ago, which produces a model of wood. And that material, which is made out of glass fiber resin, was 5 times tougher, weight for weight, under impact than the best steel. That was with a drop weight test. And that was entirely using the structure of the material.
Yeah. So this is my daily bread. Everything that Julian has just mentioned. So I'm 100% on his side when describing this, and I think we tend too much to focus on the design of the structure, but what we should start doing is trying really to design materials and trying to architect this microstructure to deliver the performance that we want. So it's and this lack of control over what happens when you have a crack initiation, and you're looking at how that damage would eventually develop, and whether it would lead to a catastrophic failure of your structure or whether it would preserve the structural integrity of your component, is basically what at the moment forces us to over-design the components, because we have complete lack of control on how damage propagates in the structure. Usually when it happens, it's very brittle, it's very sudden, it's very harmful. So what you do is that you try to avoid in any possible case that damage would ever form. And you basically overbuild, which leads to overconsumption, which leads to heavier structure. So you're not really developing an efficient, a truly efficient structure. And this is where I think biomimicry could really be a game changer and an excellent fit to advance the industry in terms of material design.
So I have a couple of different thoughts on this. And the first and foremost obvious thought, of course, is getting this to scale, and across the valley of death. We can create these materials, we can get the structures right, we can test them on the bench. When you're taking it to full automotive scale production, even if it's in small lots or in something like I mentioned earlier, and used in high performance racing, you're talking about tens, if not hundreds of millions of dollars of capital investment, to be able to get that to scale. So that's an obvious statement. I'm not blowing anybody away with that particular insight, but the path by which to get there, to talk to the large primary materials manufacturers and then talk to the people that are going to be doing the process and the integration, the design, is a very detailed process. And there's some very interesting enabling technologies along that pathway. And so one thing that we don't talk enough about when we're thinking about nature design materials is we're not simply taking shark skin and making shark skin and stretching it on airplanes. We're replicating its structure, in an existing material. But what we have seen really in the last 10 years is a revolution in material design. So at the molecular level, using AI, general AI, or targeted AI in a materials informatics type of solution to go through millions of potential chemical compositions. Now you can have a meaningful conversation with a primary material production company. So if we are looking to something that's more chemical oriented, right? In the composites area, the good news is you can batch data very quickly. And you can run very quick sample studies to be able to create large data repositories, to be able to run those machine learning engines. And so you already see now in Corning and Dow, BASF, running very sophisticated materials informatics groups. And that's a power shift away from the traditional way to design or discover or patent a material. Material Genome Initiative did a very good job of organizing the community, but it's ultimately a commercial scale issue. And there's been a very robust startup space focusing on materials informatics, but a lot of the innovation is ultimately going to reside with the materials companies. They're looking to the biomimicry community and the biology design material community to tell them fundamentals before they can make those big investments in material.
Very inspiring points. Julian, you have been talking to us about how many engineers didn't get the biology right in biomimicry projects. Hearing that about material and genome projects and all the structural design development, do you think that people can get a better chance to get the biology right?
So I would say that one of the problem that and sometimes the mistake that we do with when trying to use a bio-inspired approach is trying to just copy paste from nature to engineering, and that is completely the wrong approach. What then biology should help us with is really to understand that structure function relationship, how the concept that didn't reach that stage of the evolution were discarded, why were discarded, and try to understand then how we reach that final solution. They are complex organisms. They do not function just from the structural point of view. They also have different functions. So it's not just a source of inspiration for a multifunctionality, but it's also a way to really try to understand what's the relationship between a feature and a function, and then try to apply that same type of relationship to engineering. So never copy paste. If it's a copy paste, then it's just pure marketing and nothing more.
Yeah, sounds about right. Yeah, I totally agree.
One thing I must insist upon, and that is that biological materials are assembled. And I think it's all very well throwing vast amounts of technology at trying to understand the way biological materials are made, but I think you can also get some ideas from looking at traditional or even vernacular methods of making materials, because on the whole those are low energy methods, but also they don't concentrate on the basic materials. They are looking at the way those materials are, those bits of materials I should say, those subcomponents are actually put together. Coming back to the mother of pearl, yes, okay, you think mother of pearl is wonderful stuff. How the hell can I make it? People have been trying to do it for a long, long time. The simplest method I've come across is to use a paper making machine. And there you've got a system which is putting together layer after layer after layer. It's a very, very well tried technology. Paper making is at the top of the sort of S-curve of being a technology. In other words, you have to keep a paper making machine running 24/7 in order to make a profit. Now, if you include some clay in with the furnish at the wet end of the paper machine, you can make a layered material which is clay and paper. So in other words, clay and cellulose. That sticks together very well. It is very, very tough. It's getting on for as tough as mother of pearl. It's also, because it's clay, it's fireproof. Despite the fact that you have paper there, the clay is held together because it's got very high ionic charges on the surface. So you've got a fair amount of cohesion built into the chemicals as well. And that is a very effective material, very cheap to make. We have the technology available now. We don't have to go into all sorts of complex and patentable, highly patentable systems to be able to make it. I suspect that if we think a bit more about this stuff, we'll find other ways in which we can make some of these apparently complex materials in a much cheaper way.
So naturally, Julian, I'm all ears. Yeah, there's a cultural separation between the folks that are going to do this at scale and what a lot of what we're exploring right now, and I think ultimately that's where we tend to come to loggerheads. Is who puts the money forward to make the investment to go to scale, and what's the qualification process, that they can be reliably looked to do the testing, that they can continue to move that into a commercial application. I don't have answers for that. Those are all observations, Julian.
Well, as I said in my opening comments, when you wanted to know more about materials, the first thing that needs to be changed is the mindset. And I know that because as a biologist, I spent the last 8 years of my career working in a mechanical engineering department. They invited me to go there because they thought it was going to solve all their problems. And actually, they didn't realize what problems were. Their problems were mostly that they'd been educated, that they know all the answers. That's a big problem with engineers on the whole, but those answers are on the shelf. They are not in their minds. And so a lot of engineering is simply based on teaching people various problem-solving methods without teaching them how to define the problem in the first place.
What would be a more appropriate way to kind of analyze a problem than
the way biology does it? And this has huge advantages. Biology tends to I mean, you have an organism which works, right? Then the environment changes around it, and it might be the biotic environment. There's something else which wants to come and eat you, or it may be what we're going through at the moment, which is some form of climate change. Anyway, that means that some of the mechanisms that biology has available aren't going to work quite so well. And you can use that to define a problem in terms of a trade-off. Now, this is very important, because if you start to define and solve problems as trade-offs, then you need to know where you are, you need to know where you want to go. You need to do that sort of definition just as much with engineering, and that's the way the system that I've been building up works, actually. It's taken from an engineering problem-solving approach. But if you do this properly, there's a huge advantage, because when nature solves problems in this sort of way, it doesn't neglect the previous solution to the problem, it integrates it. So that instead of moving from one place to another on your function curve, your function graph, you're moving along a curve all the time, and you can change the influence of the two halves of the trade-off to produce exactly what you want. But that also means, and it's a bit difficult to do this without a slide, I'm sorry about that, but that also means that you're adaptive. This is one thing which engineering sadly lacks, I think, because you don't normally build in either the ability to change as you go along, but you don't also build in the sensors which you need in order to, and the control systems which you need in order to implement and control the change. So the idea of having an adaptive automobile, for instance, which may be able to change its streamlining shape according to the speed it's going at, as an example. I mean, fish do that sort of thing. Then you're losing out. You're designing a system which is very much optimized for maybe one range or one small range of use, whereas it could be designed for a much larger range of use if you could take in some of these ideas about optimization along some line of variability defined by the trade-off that you're trying to solve.
Yeah, Lorenzo, you mentioned that looking at biological organisms in terms of relationships and context, do you see many similarities in what Julian said in terms of the different ways of looking at things?
Yes, as I said, it's really trying to understand the function of a certain feature. Like, for instance, if you look at and just to give you a couple of examples, but you can find it in basically everywhere, in the cortical bone as well as in the bamboo. You can find bundles of fibers which are structured into hierarchical levels. So basically what happens when you pull them in tension, you don't have a neat fracture of the fibers, but you rather have the bonding of these bundles at different hierarchical levels. And while pulling this material, that the bonding causes a pull out, and pull out causes friction, and friction causes a lot of energy being absorbed during the process. So you get a very progressive failure instead of a brittle and catastrophic type of failure. So you could try and replicate this with the fiber reinforced composite materials. Since you could take toes of fibers of different sizes and try to pack them together to create this hierarchical structure. It doesn't make sense. It's not viable. It would never end up into an actual product. But what you can do is try to introduce some sort of defect in the structure that, when you pull the material in tension, would lead to an early failure that would steer a crack and activate this hierarchical type of pattern inside the composite. And this has been part also of the research activity that I did in the past at Imperial College London. And you can improve fracture toughness of carbon fiber material by a factor of 3 compared to so 300% increase compared to a conventional solution that doesn't have these embedded defects that actually activate these complex pull-out mechanisms. So again, not just mimicking, but really trying to understand what's the function of a certain feature, and try to isolate that function as much as possible to achieve what you want to have in your engineered material.
I think we need to be about talking about hierarchy, in that some of that comes simply because the machines which make biological materials are that much smaller than the structures they produce. I mean, single cells, and that therefore hierarchy becomes automatically necessary. What I think needs to be looked at rather more is the way in which those areas that you're talking about, which might initiate fracture, are distributed throughout the structure. Because you need to look at what their zone of influence might be. Under a certain load, how big a crack is going to be formed before the crack is either stopped or before it meets something else, or etc. And under what loads will that crack develop. What you can then do is to distribute those areas throughout the piece of material, so that instead of the crack just going through part of the material and the material on either side of it being totally untouched, you need for the whole thing to fall apart, and then it'll obviously absorb vastly a larger amount of energy before it does fall apart. I reckon you should read a poem written by a guy called Oliver Wendell Holmes, an American poet in the last but one century, called The One Horse Shay. And this was about a shay, or a carriage, which was made out of wood, but it was beautifully made out of all the right woods and everything else, and the bits were joined together in the proper way. Joints are the most difficult part of a structure, as you know. And he said this will last for 100 years. And of course, on the evening of the 99th day, it fell apart into a cloud of dust. Now, that is the perfect structure. You know exactly what's going to happen to it, and it performs up to its best right until the very end. You can see this sort of thing in, well, what used to be a fairly common structure, and that is pit props in a mine. And you also get it in the wings of gliders, for instance, which are also made of wood, or other ones which are made of wood. Now, every time you hear a click, then that is a fracture event occurring within the material, but it's not dangerous, because so many fracture events can occur without the material itself really falling apart. It's when the pit prop stops speaking to you that you know the problem is going to arise, because at that point, all the available fracture events have disappeared. And it's 99th year.
Okay. Hey, this is Trisha here. I'm wondering if the panel would entertain questions from our audience.
Yeah.
Okay, great. Thanks. So, Britt, go ahead.
Wait, hang on.
Wait, hang on.
I got it. And then go.
Good. Okay. Hello. I don't know if you were listening on Wednesday, but we had Billy Allman in, who mentioned that cars have over 30,000 parts, and that modularity will be key for the future of transportation. So one of our virtual attendees is curious of how do you think modularity will influence future vehicles, and how might that be achieved through biomimicry?
Right. Yeah. So I'll take the first swing at this, and I'm going to come back to, the first principles of design and having nature-inspired design. Absolutely, there's 30,000 parts in a car today. Just like in aerospace, parts reduction is coming to automotive, and that's where a lot of the automotive companies are looking to nature, with generative design tools, to say, how do we take something that is 28 parts, on a complex door or a handle, and wick it down to one printable part, and then that fundamentally changes the manufacturing flow path as well. And then I have to question. I'll come back. I question how many cars are going to be made going forward. We're going to see a decline in volume, and we see a decline in volume. You can get a little bit more clever in your manufacturing infrastructure to be able to introduce things like metallic or plastic 3D printing that's inspired by design.
Yeah, if I can add on that, so we see, for instance, modularity already in which is pretty easy to realize in electric vehicles, right? Because you can have a simple platform. You can scale up the battery pack. You just increase the width and the length of that platform, and you build up from a car to a van to larger and smaller sizes vehicles. So that is, I think, already happening. When it's about decreasing the number of parts in these structures, and you see it in aerospace, for instance, where we are trying to move from fastened structures to bonded structures, and now even to a one-piece wing structure. Now, you definitely reduce the manufacturing steps. You make it potentially easier to manufacture and faster to manufacture with the methods that we have nowadays. But one thing you need to bear in mind is then they become very critical to repair when they damage, and they become very critical in general when they damage. Because, in an assembly, if you have a damage on a panel, and that panel keeps cracking, the crack, when it reaches the edge of the panel, the crack will stop. But if you have a continuous material, then there is nothing that would stop that crack. And hence, where you could have a failure of your structure that is relatively safe, you just land with your aircraft, you change the panel, and that's done. It could lead to something which is more serious and harmful. So that is really where biomimicry can help us. And, you can design these materials, so not the structure, but the material, to actually being able to function as a crack arrest or as an assembly feature that would help you to avoid a failure where you don't want it to happen. So, yeah, my 2 cents on this.
Great, thanks. Do we have any?
There in terms of biology, one of them is the graceful failure, which you have with a very tough material. It's not all going to collapse at once. And the other one is, of course, health monitoring, which again you get in biological systems where you've got registering pain and things like that. So there are some ideas you can take from biology, but whether you can, as an injured car, go and run away in a cave and repair yourself is another matter entirely.
Great. We have time for one quick question. Does anybody in our audience have a question? Nope. Any online?
Yeah, but I think everyone.
All right. If the panel has any closing statements or any last things they want to say, and then we'll wrap up because we have a hungry group here. It's lunchtime here, so.
Well, I don't have any particular closing statements. And I don't want to get in the way of lunch, but you really invite the invitation to join you today.
Yeah. All right.
Yeah. Thank you very much.
Thank you all to our panel. It was great conversation. Sorry for the technical difficulties, but we gleaned enough great information. And so thank you so much for your time.
Yeah, thank you.
Thank you.
Bye.